Alright, so what's going on, guys? Today I want to go over a little bit more of some quantum mechanics. Specifically, I want to go over how we can read quantum mechanical equations. This isn't something that's really gone over a lot and in your typical quantum mechanics class. And so oftentimes students will find themselves stuck if they want to go on to something a little bit more advanced, or if they are having a hard time understanding some of the concepts that might show up in their textbooks, for example. And this also doesn't just apply for quantum mechanics. This can apply for any sort of high-level math course. Being able to read equations almost like you're reading a sentence is vital, so that you can kind of make sense of what the equation is trying to get at. Because oftentimes we're just told an equation, or we see an equation in a textbook, and we don't really know what to do with that equation. We don't really know how to read that equation, or how to make sense of it. And so in this lecture, I want to talk specifically about matrices, and how matrices are very important in understanding and how to read equations, specifically in quantum mechanics. And I want to do this in the light of something that we call an expectation value. And so let's get right into this. Again, I told you I'm planning on paralleling modern quantum mechanics by Sakurai, but occasionally here and there I'm gonna introduce a video where it might deviate from the path a little bit. It might deviate from the context of the book. But without further ado, let's get right into this stuff. So I want to first consider a standard operator. So in the past video, I talked about stressing the operator view of things, and how operators are sort of the essential mathematical objects that are vital in understanding exactly how we can begin to make sense of quantum mechanics. And so let's start here with an operator. Like, this is typically a way we can denote the operator is just some arbitrary operator O with this tail hanging off of it. And earlier we talked about this operator can act on a state, and it will produce a different state. And if we recall from the last video as well, states can be represented as vectors or functions. And so we can think of these as vectors. So these vectors that describe a state, and an operator that sort of operates on that state to create a new state. Okay. Now this is a little bit unconventional, and you don't really see this happen a lot. But what I'm going to do is I'm going to basically just I'm going to write something like this. Okay. So we have something that looks like this now, and what this basically is we're taking this state, we're operating on it with this operator right here, and it's being transformed into this state. So these two statements are kind of the same thing. Okay, so I'll put an equal sign there. These two statements are kind of the same thing, where we have a state here being translated into this state here. Okay. And we can, in quantum mechanics and quantum mechanics textbooks, we can see that this is often told that we're often told that this thing is a matrix. Okay, and so this is a matrix, and the elements of this matrix look a little bit something like this. So in the first element here, we have something that looks like this, perhaps. We have the first component of this state vector. All right, and it's being operated on by this component of the matrix. Okay, and we have this state vector here operated on by that matrix, or this matrix's operator is operating on this state here to give us this state, and I'll put a prime right here as well. Okay, and we can basically fill this out for an entire matrix. Okay, so it would look something like this perhaps. And you can see the structure of this matrix now. It looks a little bit something like this, and I'm just completing the matrix a little bit with these dots. Okay, so the diagonals are all gonna have the same indices on them, and so what we could say is that if we want to get rid of a little bit of clutter here, this thing is 1, 1, 2, 2, 3, 3, for example, and then this operator here would be 1, 2. This one here would be 1, 3, and this one here would be 2, 3. Okay, and then this here would be 2, 1. This here would be 3, 1, and this here would be 3, 2. Okay. So these are the degrees to which, these are the elements of this matrix. These are the degrees to which the final state, the components of the final state the components of the initial state have been transformed into the components of the final state. Okay, and so if we take this one, for example, this element right here, this is the degree to which the first component of the initial state is transformed into the second component of the final state. And we can think of it like that. Okay, we have to be able to think a little bit abstractly as well, because this matrix can be any size we want it to be. It could be a 4 by 4 matrix. It can be a 5 by 5 matrix. In that case, we're operating in 5 dimensions. And as I've said in the past lecture, is that the states can be multidimensional as well, depending on how many points we define on our function. We can have a 5-dimensional vector. We can have a 6-dimensional vector. This and this is just an example here of a 3-dimensional object that would transform a 3-dimensional vector. Okay, and so if this thing can be operated on by psi 1, psi 2, and psi 3, and what we have here is basically this side of the equation. And what we would get is psi 1, psi 2, and psi 3. But we have all these primes on there because those are the translated components. Okay. And so we could think of an operator as like a matrix, and a matrix is like a function, right? And now there's a couple of properties we can understand about this matrix, depending on how it does this translation. It will we might be able to discern what types of what type of transformation this would be, or what type of I'm blanking on the word. What type of operator this would be. And what I mean by that is we have this matrix here, or this element of the matrix here. If this thing was equal to this thing, then this would be symmetric. These two things would be symmetric. If this was not equal to this, but actually the opposite of it, so the negative of it, if operator 1, 2 is the negative of operator 2, 1, then we would call it antisymmetric. Okay. Same thing here. If we have this here is the same as this one here, those would be symmetric. And if they're the opposite or the negative of one another, then it would be antisymmetric. Okay. We'll go into antisymmetric and symmetric properties of matrices a little bit later, because that's somewhat a little bit more advanced than I want to go into right now. But again, if we take a look at these two, if those are the same, they're symmetric. If they're opposite of one another, they're antisymmetric. Okay, and again, this thing operates on this matrix, on this vector here, on the state, to transform it into a new state, which is this state right here. Okay, so let's take a look at a tangible example here, and this is probably one of the more simple examples, and I'll get into more complex stuff later, but let's take a look at the Kronecker delta matrix. Okay, the Kronecker delta matrix, so Kronecker delta matrix, we can think of it as maybe looking like this. So we have our state, our final state, and then our Kronecker delta looks like this, and then we have our initial state, and this is a matrix element again that looks like this. So Kronecker deltas down the diagonals like this, and the indices on the Kronecker deltas there excuse me, 3, 3, and then these are all 0. Okay, this is a special matrix. It's not really, it's symmetric because 0 is the same as 0, but it's a unitary as well. And so what do we mean by a unitary matrix? Well, this is the same thing. A unitary matrix is 1, 1, 1 down the diagonals, and then everything else in here is 0. And this could be, in our case, we're just looking at 3 dimensions, but we can also look at a larger dimension Kronecker delta symbols, and how they might translate a state from its initial to its final state. Okay, and so we have the interesting thing about this Kronecker delta here is that it's just ones down the diagonal, such that if we were to multiply this by, or if we were to act on a state with this element here, we would just get back the original state. So in other words, the state didn't change. Okay, that's a special thing about this Kronecker delta. And we write the Kronecker delta symbol if it has n m indices. So this would be the rows. So and this would be the number of columns. Or my bad. You can write this out. You can write this out, and this would be this is a matrix. This is a matrix, and what it equals is 0 if, it might be easier actually. I might write it like this. I'll go like this, just to make things a little bit easier to understand. We have final, initial. So if the final does not equal the initial component, so if the final component does not equal the initial component, then this is going to be 0. It's going to be 1 if the final component does equal the initial component. Okay, this is the Kronecker delta symbol, and it's a very important function, and it's a very important matrix, because it means it's the one matrix that tells us that if we apply this transformation to a state, then we get nothing. We get nothing in return, and that's an important concept to understand. Okay, so again, this is the Kronecker delta symbol. You might see it as MN in textbooks or something like that. You might see different indices here, but this is again the Kronecker delta symbol And we could sort of think of it as an operator. This thing operates on a state to give us another state. Okay? So with that being said, I want to segue a little bit into how we can begin to make sense of some more interesting equations that we might come across in a quantum mechanics textbook. And again, I'm using the modern quantum mechanics textbook by Sakurai. And typically we see something that might look like this. So say we have a state, psi, and we might see something that looks like this. Okay. Okay, so how do we make sense of this? So this here, we have to understand what this object is. Okay? And in order to understand what this object is, we have to be able to understand what the difference is between the inner product and the outer product. Okay, so the inner product, if you remember, so this is an outer product. Outer product. And so the inner product, if you remember what the inner product is in your basic vector calculus class, or in your basic in your basic general physics class, an inner product basically tells you how much two vectors are similar to one another. Okay, so again, I'll write this out. So the inner product it tells us how much two vectors are similar to one another. So it measures similarness or sameness between two vectors. So sameness, I'll just write something like that. Sameness between two vectors. And what that looks like, it looks like this. So say we have a state, psi. Actually, I'll do phi to be a little bit more consistent with my notation. This is what an inner product looks like. So we can get a number out of this. And in this particular case, if this vector doesn't change, in other words, if the final vector is the same as the initial vector, then our inner product is going to be 1. Okay? That's just a number. So we've acted on, you can think of this as we acted on you can think of this as how much one state, the initial state, is the same as the final state. Okay? If the final state, say for example, you rotate a vector just by a little bit, okay, the components of the x component, for example, of perhaps your rotated vector is going to be a little bit less than the x component of the initial vector. So for example, say our initial vector lied on the x-axis, and then we rotate it, and it looks like this. Okay, well, now we have that the x component of this final vector is a little bit less than the x component of the initial vector, and that's going to be taken into account when we do the inner product. Okay. And now there's formulas and everything for the inner product in your basic physics class, but I don't really want to go over those. That'll be reserved for like classical physics or something like that. In quantum mechanics, this inner product is basically done like this. Okay. So now, how about the outer product? Okay. Well, the outer product, it's not really going to measure sameness. It's going to yield a different object though. So here we went from a vector, we went from vectors to a scalar. Okay. In this case, we're going to be going from vectors to a matrix. okay? And what this matrix is going to look like, so what this matrix is going to look like, if we can think of this as this vector here is in your standard, it's in your standard vector format, column vector, and this one here is in your standard row vector. That's what your bra vectors are going to be like. They're going to be row vectors, and then your standard vectors are just going to be your standard column vectors. Okay, and we call this beta 2, beta 1 actually, and beta 2. Okay, and so what we get is we want to multiply A1 by all of these. Okay, so we have alpha 1, beta 1, and then alpha 1, beta 2, and then alpha 2, beta 1, and then alpha 2, beta 2. And this is our what we get. Okay, so here if we were to do this for the inner product, if we were to do this for if we were to do this sort of row column notation, this would be the same thing as saying, well, we said this was the row vector, so that's alpha 1, and that's alpha 2, and then we have our beta 1 and beta 2. Then we can do matrix multiplication on these guys. In this case, it's beta 1 times alpha 1 plus alpha 2, because this is a row vector. We're not reading across like we read here. We're sort of reading down, and we have to add those. Okay, so that's going to be beta 1, alpha 1, beta 1, alpha 1, plus beta 2, alpha 2. So we're multiplying this by this and this by this. So that's going to be beta 2, alpha 2. Okay? And this is a number because we're adding these two things together, and that number is 1. So here we get a scalar, and here we get a matrix. Okay, so now let's begin to think of what this object might look like right here. So this is an outer product, and this is an inner product. This is an inner product. So there's multiple interpretations we can provide on, or we can impart on this object here. That's the inner product, and that's the outer product. And if these two states here, these two phi's are the same, then we get an outer product, a matrix, which is unitary. Okay, if they're the same. Again, so this is sort of a sameness measurement, but in terms of a matrix. This is a sameness measurement in terms of a scalar. Okay? And so let's think about now, so let's think about now what this object might look like. So we have phi equals, now we have this, now I'm introducing this summation notation here, and I'm just going to basically put the same thing in here, like that, okay, and we'll put indices on this, and we want to sum all those indices to, we start from 1 and say we want to go to 3. Okay. So, so how can we make sense of an object like this now? So what we're basically saying now is that we have we're basically writing a vector. We have a vector here in terms of another vector, okay? So, and this other vector is an interesting one because here we have an inner product. Here we have, you could think of this as some initial state, and it's being compared with some other state, okay? And we're taking an inner product on that, okay? But then these two things here, these are a matrix. So again, like I said, there's multiple interpretations we can impart on this object, but the important thing here is that we're writing this sort of final final actually I won't do that. We're writing this in terms of a different set of vectors, okay? And those different sets of vectors, for each vector, for each state, there's its corresponding bra state, or its corresponding bra vector. And we have we're basically creating a matrix out of two completely different vectors to solve to write this vector in terms of those vectors, okay? And this is an extremely powerful tool, and it's especially extremely powerful when we're reading stuff like quantum mechanics, because perhaps, and this is one of the reasons why, perhaps this vector here is a little bit hard to write off on its own. You can't really write it in terms of it might be a complicated vector, and it might be easier for us to write this state out in terms of some simpler vectors, okay? And those simpler vectors are these vectors, these vectors here, okay? So this is sort of a way of writing a vector, maybe it's writing a state that might be complex and breaking it down into sort of a non-complex state, in which these vectors here that we've chosen are a little bit easier to manage, okay? So again, what do we have here? We have an inner product, an outer product, and this all helps us in understanding this complex state here, okay? And when we're summing, this is basically the same thing as 1, 1, like that, plus 2, nope, that's the wrong way. It's going to be a 2. That should be inside the brackets. And then a 2. And then that state like that. And then plus 3, and like that, okay? So this is the longhand version of what the summation looks like. So we're starting from 1, we're going to 3, and all of these here are outer products. So this here is an outer product. There's an outer product. This here is an outer product. Oops. So this here is an outer product, and this here is an outer product. Okay, and we are all writing the different components, and if I was to be actually a little bit more complete here, we basically have this unitary matrix. This is a unitary matrix because these two are the same, these two are the same, and these two are the same. Okay, and we're writing this state in terms of these simpler states. Okay. So that's the outer product and the inner product. Now, I just want to allude also to a tensor product. Now, a tensor product is basically the same thing as an outer product. Okay, and so how can we quickly? So one of the next question I want to tackle is sort of I want to take a look at these objects in particular again, but look at them a little bit differently. And this is going to help us not just for quantum mechanics, but this is also going to help in general relativity a little bit. Okay, so those objects. So here we have a ket vector or a ket state. Okay, and here we have here we have its corresponding bra state. Okay, so this can be thought of as just a vector. Okay, and this thing can be thought of as something else. So what is that something else? In general relativity, we call it a covector. Everywhere we call it a covector. So this is a covector. Now I can't remember if I alluded to this in my first video, but again, since I'm on no time limit or anything like that, this isn't a class that you're taking at university. I'm going to take all the time I need to sort of hammer home some points here so that you can really understand what's going on. So this is the same thing as a ket vector, and this thing can be thought of as a bra vector. Such that when the ket vector is applied to the bra vector, we get 1 if the two states are the same. Similarly, a vector with a covector. Okay, and so there's different notations here. We can a vector, your standard vector, is going to be in column notation, and your standard covector is going to be in row notation. Okay, so we have those objects there. And if we remember the Pythagorean identity, the Pythagorean identity is we have some triangle. This is A, this is B, and this is C, where each one of these is the magnitude of each vector, of the magnitude of each side. If we remember Pythagoras, then a squared plus b squared equals c squared. Okay, so c squared here. So what's interesting here is that we figured out to figure out exactly what the magnitude of this vector is, of what c is. We're basically squaring it. There's something very interesting about squaring something when it comes to quantum mechanics. Squaring something renders it like an invariant. It renders the object, it extracts the object's invariant nature out of it. So whenever we square something, or not anything, but whenever we do this squaring process, we want to begin to think, okay, that we might be thinking of something that might be invariant. This is something that doesn't change under any coordinate transformations. Okay, we could think of A and B as coordinates. Okay, and so when we square everything, we get this object again that doesn't change with respect to any change in the coordinates. And I'll go into this a little bit deeper as well when I open a playlist on general relativity. But the interesting thing here is that, okay, this is squared. What happens if we square an imaginary number? And so in quantum mechanics, we're dealing with imaginary numbers, right? So an I squared is going to give us -1. So squaring not only sort of gives us this interesting property of sort of discovering a magnitude of a vector. If we want to figure out the magnitude of this vector, we have to square it. Okay. So this is the magnitude. So again, squaring something is squaring it. It's vital. Okay. This Pythagorean identity gives us this notion of squaring. Okay. When we square an imaginary number, we get a real number. And remember, the only things that really exist in the real world are real numbers. Okay. So when it comes to quantum mechanics, and we're using I a lot, we have to square things. We have to square things if we want to discover measurable quantities in the real world. Okay, so again, squaring, again, is very, very important when it comes to understanding quantum mechanics. And so then we can begin to think of something like this. Okay, so here is our covector, and here is our vector. This is the same thing as squaring. If you think about it, even if these were complex numbers, we'd still be squaring the real components of those complex numbers. Okay, this process sort of siphons out the imaginary stuff. So this process, it takes out the imaginary numbers. This process takes out the imaginary numbers, and at the same time it's squaring, because we have this times it's the same thing. And it's the same thing as squaring. Okay? And so we have these. So when we apply a covector to a vector, we're scaling, we're squaring we're squaring the vector, and we're getting an interesting property out of that vector that is ultimately going to be invariant. Okay, it's not going it won't change under any transformations. Okay, and this in quantum mechanics is equivalent to a probability. So squaring, taking out imaginary numbers, and a probability, they all sort of have the same rationale behind them. Okay? And so we have this notion of squaring now, and I'll go back here also just to go over a quick summary. So we talked about operators, okay, and we talked about their components, okay. We talked about an example, the Kronecker delta, and again, this is what the definition of the Kronecker delta in terms of initial and final states, okay. And then here we talked a little bit about how we can make sense of this object here, how we can understand writing a vector in terms of other vectors, okay. And then we went over a little bit about the inner product, okay, with respect to this framework, the inner product, and then we talked a little bit about the outer product as well, with respect to this framework again, okay. And then we sort of generalized the outer product to its various components, okay. And that's this right here. And then we went over squaring and why squaring is important in physics, and especially why it's important in quantum mechanics. This here, I'll put arrows right here. This here is quantum mechanics, because again we have I's in quantum mechanics, and we'll see why we have I's in quantum mechanics, and especially why we have I's in quantum field theory later. I spent like all last night trying trying to figure out what a good way to teach why I is so important in quantum mechanics, because oftentimes we're just told, put an I there, this is quantum mechanics. Okay, I is extremely, extremely important. Okay, and the reason why it's important in quantum mechanics, I think, deserves its own lecture. Okay, again, I is the square root of -1, and when we square a state that consists of I, excuse me. When we square a state that consists of the I in it, we are basically siphoning out those I's. Okay, that's the same thing as squaring, and in quantum mechanics that gives us a probability. Okay, again, this is all very basic stuff. I haven't really actually dived into the book yet. I just feel it necessary to provide ourselves with the necessary information in order to actually begin to understand some more complex equations and be able to understand some more complex notation and more complex ideas in quantum mechanics. This is all preliminary stuff, and it's all very, very necessary and very important to be able to understand how all of this is connected with one another. Because after the next few lectures, things are going to get really complicated pretty quick. Okay, I intend to go pretty quickly into some more advanced topics in quantum mechanics, but I also want to do it at a pace that's easy for you guys to understand. And so I'll leave it at that for right now, and I hope you've enjoyed this video, and I hope you get a lot out of it, and I'll see you in the next video. Thanks.